So the following functions are continuous on their domain. So, for example, polynomial functions are continuous on their domain. We already saw rational functions are continuous on their domain. Root functions like square root of a plus x, or say ax plus b, so on. Trigonometric functions like sine, cosines, tan, etc. They are continuous on the domain. Inverse trigonometric functions are continuous. Inverse trigonometric functions correspond to what? What are the examples of inverse trigonometric functions? Examples are sine inverse x, cos inverse x, tan inverse x, so on. Exponential functions 2 to the power x, e to the power x, etc. are continuous on the domain. Similarly, log functions, log of x base a, these functions are continuous on the domain. So we want to see what kind of functions are continuous. So now there is few more things about continuous functions. Namely, if you take two continuous functions, f and g, both are continuous at a. So given that f and g are continuous at a and c is any real number, fixed real number, c is a fixed real number, so such a number is called constant, then we have f plus g is continuous, f minus g is continuous, f times g is continuous, constant times f is continuous, and f over g is also continuous. So these functions are continuous. So these functions until here are continuous at a as well. And in this case, f over g, we need something extra. That is what is continuous at a, provided what? G of a is not 0. So another interesting thing to know about is the continuous function is the following. If you have f is continuous at b, so you have f continuous at b and limit as x goes to a, g of x is b, then you can bring the limit inside the continuous function. So the idea is you have limit as x goes to a, f of g of x is going to be f of limit as x goes to a of g of x. And your function f should be continuous at this limit for this to happen. And if this limit is b, as x goes to a, g of x is b, then this is going to be f of b. Okay. So here, so let's evaluate this. So now you can think about this as f of g of x, where your f of x is e to the power x, and g of x is 1 minus x. Right? So f is continuous on all real numbers. So this limit is going to be, if it exists, is going to be so now you can do everything, compute the limit at the exponential. So this is going to be e to the power limit as x goes to 0. You can rationalize it because it's 0 or 0 form. One minus x minus 1, because a minus b times a plus b is a square minus b square, x times 1 minus x plus 1. So this 1 and 1 will cancel and the x will cancel out. So this is same as limit as x goes to 0 minus 1 over square root of 1 minus x plus 1. And as x goes to 0, that goes to minus 1 over 2. So this is the limit of this function. Note that for this to happen, there are two things. We can bring the limit inside only if what? F is continuous at b and limit as x goes to a, g of x is b. So we can bring this inside only when E is continuous at this limit. Yeah, so this limit should have existed at the first place to do this. All right. Yeah. So we are basically saying if this limit exists, this should have been this guy. And then we worked it out and we say, oh, I see, the limit exists and therefore it's okay, or it was okay to do that. All right. Otherwise, it wouldn't have been okay to do that. So similarly, if we use the same concept here, if we use this, result, you can prove the following. You can prove limit as x goes to a. So suppose f is continuous at b, that means what? Limit as x goes to b of f of x equals to f of b. And suppose what? G is also continuous at a, that means limit as x goes to a, g of x equals to g of a. Now we want to talk about the composition of this. So what can we say about the composition of two continuous functions? So if f g is continuous at a and f is continuous at g of a, then the composition is continuous at a, right? So that you can see limit as x goes to a, f of g of x. Now we are claiming that this is continuous at a, means we want to show that this is same as f of g of a. So let's see, why is that true? So this is going to be f times limit as x goes to a of g of x, right? From the earlier theorem. And this is going to be g of b, g of a, because what? G is continuous at a. So you get that the composition of two functions is also continuous. So are there any questions, comments so far? Let's ask the following question. So f of x equals to x to the power, say, 10 plus x minus 1. Does this function has a 0? That means, is there some real number c such that f of c becomes 0? Right? So that is a question to ask, right? Does this function has a 0? And how can we say that it has a 0 or not? Okay, so how do we basically make that argument? Well, notice the following. It's a polynomial function. It is continuous. Yeah. So if it is continuous, that means you can draw without lifting your pen. F of 0 is what? What is f of 0? F of 0 is minus 1. So at 0, the value is minus 1. F of 1 is what? 1 plus 1, 2, 2 minus 1. So f of 1 is 1. And then you have some function like this. So it will cut x-axis at some point, right? And that is why, sorry, this is not a graph of a function. Let me just draw it carefully. So at 1, the value is, at 0, the value is minus 1. At 1, the value is 1. So the function will go like that. So it will cut the x-axis at some point. That means this function has a 0. So generalization of this idea is what is called as intermediate value theorem. So what is the intermediate value theorem? So suppose you have a continuous function on a closed interval AB. So you have A, B, and you have a continuous function. So continuous function can look like that. Okay. Now, the intermediate value theorem says the following, that if you take f of a, so you take a continuous function on a closed interval AB and let f of a not equal to f of b. So we have f of a here. This is one scenario. There could be many different scenarios. F of a is not equal to f of b. Then intermediate value theorem tells you if you pick any n in between f of a and f of b, any n. So for this n, I can find a c. So for this n, there exists a c in AB such that f of c equals to n. So this is what the intermediate value theorem is. Yeah. So it says for every n between f of a and f of b, there exists a c such that f of c is n. But the function should be continuous. Note that if the function is not continuous, this is not true. All right. Say, for example, you can have a function like this. So this is your a, and suppose after say some value, this is your b, right? So this function is not continuous on the interval. So in between these values, there's nothing between a and b such that f of c is that value, right? So continuity is important. Okay. So this statement is called intermediate value theorem. All right, it's a very powerful theorem. Let's see why is it powerful. So use intermediate value theorem to say that square root of 2 exists. That means to prove that there is a real number c such that c square equals to 2. So we want a number such that c square equals to 2, or we want x square minus 2 has a 0, right? So let's take, let f of x be x square minus 2. Right? Now we need to use the intermediate value theorem. So we'll see how we'll use intermediate value theorem. So note that f of 0 is minus 2 and f of 2 is 2 square minus 2, which is greater than 0. This is less than 0. You can see that f is a polynomial function. F is polynomial, hence continuous on R, and hence continuous on any subset of R, hence continuous on 0, 2, right? Because continuous on R means it's continuous at every point of the real number, and that basically from there you can conclude that it's continuous on 0, 2 as well, the interval 0, 2. So therefore, by intermediate value theorem, for n equals to 0 in between f of 0 and f of 2, there exists what? There exists c in 0, 2 such that f of c is equal to 0. This is the intermediate value theorem, right? For here, you're using n equals to 0, right? For every n, there exists a c such that f of c is n. The same way, for n equals to 0, there exists a c such that f of c equals to n, which is 0. So if you want, which is my equal to n. So therefore what? This has a root. Yeah. So I should say has a 0 or a solution. Now let's use the intermediate value theorem to show that this equation has at least one root. So now intermediate value theorem. So let's try to do this one. So either I can try to show that these functions intersect, or I can try to show the following. Let's take f of x equals to e to the power x minus 2 plus x. Now again, I'll apply the same technique. I'll find out 2 points, at one point where the function value is positive and at one point where the function value is negative, so that I can trap 0 in between them. So let's take, that is done by inspection usually. So notice that f of 0 is what? F of 0 is e to the power 0 is 1 minus 2 plus 0, which is what? Minus 1. So that is less than 0. Now notice that what is f of 1? F of 1 is what? E minus 2 plus 1, which is e minus 1. Now that is greater than 0. Why? Because E value is roughly 2.71 something. So all I can say is that E is greater than 2 for sure. So E minus 1 is going to be greater than 2 minus 1, which is greater than 0. So E minus 1 is greater than 0. All right. So now we need, so 0 is trapped in between f of 0 and f of 1. Now, before I use intermediate value theorem, I should argue that f is continuous on this interval 0, 1. And what is the justification? Because e to the x and minus 2 plus x are continuous function. Actually, they are continuous on R, hence they are continuous on 0, 1. And if you take sum of two continuous functions, you get continuous function. Therefore, f of x equals to e to the x minus 2 plus x is continuous on. Yeah, you have to basically, whenever you want to use a theorem, all the hypotheses or requirement for the theorem should be satisfied. Yeah, it's like if you want to cook a chicken curry, you need the every ingredient of it, right? So same way, we need all the ingredient of the theorem or all the components of theorem or all the hypotheses of the theorem to be true to be able to apply it. So we got a continuous function on a closed interval 0, 1 in that case, and let n be any number. We are choosing here n to be 0. Therefore, for n equals to 0, there exists so n equals to 0 between f of 0 and f of 1. There exists c in 0, 1 such that f of c equals to 0. All right. So we have proved what we have proved. Therefore, f has a at least one real root. Yeah, there could be many real roots. Okay, real roots. But at least in this case, we are at least able to prove that there exists one real root. Later on, when we learn concept of Newton's method, we will be able to find it with certain approximation.